So today we are going to talk about, just briefly, different materials that have been researched or still under research for post-silicon technology. So we know that everything is based on silicon as of now, and we have talked about evolution of silicon device technologies, and then we briefly talked about materials beyond silicon, but in this lecture we will cover some of the materials that have been discussed, researched, and is still under investigation as a potential replacement of silicon, or maybe parallel to silicon. Some of this will be implemented. So the first one, and the most famous one, that people got excited about 30 years ago, particularly excitement increased significantly after 2010 Nobel Prize won by 3 British physicists who were successful in separating a single layer graphene from a block of graphite. So after that, actually everybody got really excited about the potential, and still there is a big portion of research community think that it is one of the potential material that can be thought of as a new material along with silicon, or maybe for some application as an alternative to silicon. So what is graphene, and what are the different forms of graphene we see, and what are the potentials? We will do a very high level discussion, not in depth. So graphene is a monolayer flat material, two-dimensional material. Why it is called flat material? Because in a graphene sheet, the atoms are all arranged in a flat two-dimensional direction. They are not like stacked on top of each other, and between pairs of atoms, they are bonded together with a very strong covalent chemical bond, and those structure or arrangement of atoms is pretty much like a honeycomb shape. Because of this, it's monolayer 2D arrangement of atoms and the bonding of chemical covalent bonding in the honeycomb shape, physically this gives the graphene a very high, extremely high tensile strength.
What's the honeycomb? You said
hexagonal.
If you, honeycomb is basically 1, 2, 3, 4, 5, 6 or 7. If you look at an actual honey, if you cut it, you will see the compartment inside where honeys are basically deposited.
Okay, yeah.
You will see basically this shape. Yeah.
Can it form its hexagonal pattern, right?
Yeah.
Can it form octagonal pattern like this?
Maybe, but it depends on actually how many bonds each atom can form. Yeah. So
It is looking like a benzene ring.
I think
Yeah.
it can, but carbon likes to do just the 3 bonds
Yeah.
because of how the atom.
So yeah, it depends on, as I said, how many each carbon atoms, how many bonds it can create to its neighbor, right? So now the question is, the benzene ring. I still remember that one course I never liked is that our advanced chemistry class, because our chemistry teachers, they were the toughest. So
Memorize every what's called the
it's not only the benzene block. Sometimes they will add like many ingredients, so the equation that becomes like a very complex benzene ring with lots of branches and trees, right?
and we need to write the name.
Yeah. So the question is why this material became so popular. Number one, because of this hexagonal pattern and covalent bond, it is very strong, and because of its 2D nature, It is ultra lightweight. Carbon atoms are very light by nature, and then since they are arranged in a single atomic layer in flat 2D surface, they are ultra weight. And because of the arrangement and the physical property of this carbon atom, they are near transparent, not 100% transparent like glass, but they are near transparent. And also because of this 2D structure, it provides very high electrical conductivity. And also this physical strength provides a very, very high thermal stability as well as thermal conductance. So all of these properties are very promising and lucrative for any electrical and mechanical device to build. So, as I said, this groundbreaking discovery of ability to single layer graphene from graphite that actually landed a Nobel Prize
I have
from
a
this.
question, sir.
Yes.
Is the same thing invented later of graphene or prior of graphene invention?
So, the concept of carbon nanotube and then concept of graphene layer, it has been there long time ago. But this group, they were successful in basically implementing that concept and successfully demonstrate that into layer. But in nature, in material formation, this tubular form of carbon as well as flat surface form of carbon, it has been there. It's not that somebody invented it, it's there, but they were able to successfully separate it. So what is graphene from chemical point of view? It's an allotrope of carbon. So for those who have taken chemistry, you remember the term isotope and allotrope. So now, what are the allotropes? Some of the chemical elements, they appear in different formation. It's the same set of atoms, but the organization, the physical orientation of those atoms can be different. And each of these different formation is called one allotrope. So internally, as I said, all the graphene, this covalent bond, those are sp2 bond, and those who are aware of the chemical bond properties, these are known as very, very strong bond, chemically and physically. And the interatomic distance of the length of this bond is about 0.142 nanometer. So if you compare graphene with any planar sheet, it's like a plain sheet of paper, and the thickness of that sheet of paper is just one carbon atom. So the other way is actually, if you do not like the honeycomb example, chicken net, chicken wire, right? Same thing. Hexagonal hoops. So it's like a chicken wire made of carbon atoms. So graphene can come in this flat 2D nature, 2D form, that is called graphene nanoribbon. And also graphene can come in tubular form. Then if the graphene, this sheet appear or you can separate, it will form a tubular form by kind of bending a graphene sheet. We call it carbon nanotube. So the carbon nanotube comes in two different physical form. One is called single wall carbon nanotube. If you have one sheet of graphene rolled into a tubular form, that is called single wall carbon nanotube. If you have multiple concentric layer of graphene layered on top of each other and rolled into a tubular form, that is called multi-wall carbon nanotube. So graphene can come in a planar sheet form, or graphene can come in a tubular form, or you can make it in tubular form or planar form. So the tubular form of graphene can come in two physical structure, single wall carbon nanotube and multi-wall carbon nanotube. And if you cut the planar sheet of graphene into narrow ribbon, we call it graphene nanoribbon, GNR. Like single wall and multi-wall carbon nanotube, GNR can also come as a single layer graphene nanoribbon or multi-layer graphene nanoribbon. So if you compare it with an electrical wire can be one solid wire or can be a bundle of many small wire, right? In modern day electrical connection, it's not one solid wire. It's actually bundle of more than one wire connected together to increase physical flexibility as well as to reduce the failure probability. Yes.
So I'm just curious with the multi-layer nanoribbon, they probably have some sort of other material between each. Is that right?
So physically, it is still very difficult to distinguish during the graphene formation whether it will appear as a multi-layer or single layer. Sometimes this layer they are not as clearly defined as it is. There will be some tangling here and there that some atom instead of connecting here it will connect with something upward. So it is not, yes, there will be some intermediate host material to hold this multiple layer. So that's why whether it's single wall carbon nanotube, multi-wall or single layer nanoribbon or multi-layer nanoribbon, you need a substrate material or host material to hold it. And then graphene electrodes can also come in other form. Fullerene, the circular or spherical form of graphene is another form of graphene. Particularly in many chemical process, it is used as a catalyst or it is used as a filler material, fullerene. And then 3D stacked 3D form of graphene is graphite. And graphite has been in use for centuries as a battery electrode or many other devices use graphite, right, in bulk 3D form. So if graphene appears in bulk 3D form, then we call it graphite. So the experimentation done by this physicist group who got Nobel Prize in 2010, that's what actually they from a piece of graphite, they did like series of processing and then finally they were able to separate one single monolayer graphene sheet. Do you know what is the easiest and the rudimentary technique they use to create graphene layer? Just buy a block of graphite and stick a Scotch tape on top of it and peel it. So on the bottom, the sticky part of the Scotch tape, some carbon atom will form, and then that is actually the simplest possible graphene layer. So, and many people, they started doing testing on those. So you put it under scanning electron microscope with probing. Now they try to send signals to see that it is behaving. You cannot guarantee that it will only stick only one layer of graphene atom, but this is the first rudimentary test. Everybody who did graphene electric and other mechanical property testing, that is the starting point. So the Scotch tape acts like a substrate. So now, why graphene became so promising or appeared to be promising? Because intrinsically, the way graphene material properties are set, it is a semi-metal or zero-gap semiconductor. What do you mean by zero-gap semiconductor? If there is a zero-gap semiconductor, then there should be a finite-gap semiconductor. So silicon, germanium, and all other group 3, group 4 material or any material element in periodic table, they have a finite band gap. The energy gap between valence band and the conduction band is called energy gap. Depending on that energy gap value, some element works as a conductor, some element works as a semiconductor, some element works as insulator. Larger the gap, it is more into insulating side. Smaller the gap, it is more into metallic side. And for silicon and other semiconductor components, there is a finite energy band gap. So graphene acts as a semiconductor, but it is or near metal property, but it is a zero band gap material. Graphene has remarkable high electron mobility at room temperature, so it can provide very high conductivity. So the mobility of holes and electrons are nearly the same, a significant improvement over silicon. In silicon or regular semiconductor, electron speed is mobility is almost 2 to 3 times higher than hole or positive particle mobility. But in graphene, they are close to each other. That means that if you use graphene as a semiconductor, you get higher current both in case of N-type and P-type conductivity. Mobility is independent of temperature, that is good thing. In any other material with increased temperature, mobility of charge carrier degrades. You have like keys like our curators. The building manager, she has like 100 keys hanging.
I always forget about the keys. I have locked myself outside my lab 2 times.
So that's why you have like multiple copies of each key. But if you carry it together, what is the point? It's the same. I'm just trying to.
Yeah, I know.
So resistivity of the graphene, that is another thing. It is in the range of 10 to the power minus 6 ohm per centimeter. And it is also significantly better than any other metal. And actually this resistivity is less than one of the best conductor, which is silver. So, and at room temperature, this resistivity is the lowest recorded if you can have a pure graphene layer. So, from mechanical point of view, so those are electrical point of view. The mechanical point of view, it appears to be strongest material for its own size and dimension. So it has a breaking strength for the same dimension 100 times stronger than the steel. Why? If you can make a 1 nanometer thick stainless steel sheet and compare it with a 1 nanometer thick graphene sheet, for apple-to-apple comparison of the same thickness and dimension, the graphene will have to sustain 100 times more stress and strain power compared to silicon. So in terms of actual number, the tensile strength of graphene sheet compared to other material of identical dimension and thickness, it's 1 terapascal for graphene. So, in the summary declaration of Nobel Prize of 2010, they actually made a very interesting, funny analogy, which is true. That, you know, hammock, you hang it in between 2 trees or 2 stands to lie in the beach, right? So what they're saying that if you make a hammock out of graphene sheet of area 1 square meter, it will be 1 atom thick, but surface area will be 1 square meter. It can hold a cat, a bulky cat of weight 4 kilogram, about 10 pounds, and the weight of that hammock will be only 0.77 milligram. Because of its extremely high strength, a 0.77 milligram weight graphene hammock or graphene sheet can sustain the weight of a 4 kilogram cat. So, which is the only 0.001% of 1 square centimeter, one square meter paper. And I don't think 1 square meter paper can hold a 4 kilogram or 10-pound weight cat. So they wanted to actually make a case for the outstanding property of graphene from mechanical point of view, just for normal human to understand. So this statement was part of this Nobel Committee's declaration. So now let us talk about compare it with conventional electrical conductor. The electrical and mechanical properties we discussed in graphene, how it compares with current day electrical conductor. This is an actual microphotograph of an integrated circuit where you see only the substrate portion is not shown. This is just a line diagram. Inside any IC, the lowest substrate, the silicon layer, that's where all the transistors, billions of transistors, they do reside. And on top of that substrate made of silicon, you have multiple layers of interconnect stacked on top of each other to form the connections between these billions of transistors to form the integrated electrical circuit, because electrical circuit means it's a close connection between devices. So physically, this is the substrate or reference level, and then on top of it you have layers of interconnect line. The way I draw it here, because the layers are directed in alternative direction. If layer 1, all the lines move from this to this direction, in layer 2, all the line will move from this direction into the slide. And the next layer will move, all the line move in this direction. So in a particular layer, no line will cross each other. Every line will run in parallel in one direction. If in layer 1 you have 10,000 interconnect line, all 10,000 wire will run from north to south in parallel. In the next layer, every line will run to east to west. So they are perpendicular to each other in terms of routing in successive line. And this is actual photograph of a real IC. As you can see, metal layer in this direction, metal 2 in this direction, metal 3 in this direction, metal 4 in this direction. This 4, 3, 2, this represents layer. Which layer the line belongs to. They're perpendicular to each other. So what is the problem with this existing interconnect structure? These are made of aluminum or copper. Because they are in multi-layer structure, and there we need to have some vertical connection, and we have the horizontal wire running in perpendicular direction. So vertical connections must also similar material to the wire. But then you need some intermediate glue material to connect this horizontal line with the vertical line. And then that vertical line finally is connected down to the silicon layer. So you have silicon making a contact vertically with a metallic line. You have metallic line in one layer making a vertical contact with a metallic line. So there are some transition material you need to make that glue as well as conducting connection. You cannot put a glue that is insulated, right? The glue has to be also conducting, so that signal can travel from silicon to vertical line to the next layer to vertical line to the next layer, right? So because of the materials mismatch, aluminum, copper, and intermediate material, each one of them has very, very high resistivity, significantly higher than graphene. Also, each one of them different thermal productivity, thermal conductivity and thermal expansion. Some of them will expand more, some of them will expand less with higher temperature. So it will put tremendous stress on the junction, intermediate material, and intermediate material will have its own thermal property, own thermal conductivity. Due to these mismatches of thermal and electrical as well as mechanical properties, plus its high resistivity and lower thermal tolerance, at high temperature and high power, these interconnect layers become very, very hot. And that was the reason your laptop, your cell phone, if you run it too long, you feel the temperature. 75% of the thermal stress or heat generated by ICs are coming from this interconnect layer. Only less than 25% are generated by the silicon layer. And this heat is encapsulated in this layer of interconnects, which is on the upper side, it is covered by silicon dioxide, and the lower side is also covered by silicon dioxide and silicon layer. So the heat is trapped. So that's why even though theoretically the transistor can run at 30 gigahertz, even 100 gigahertz, practically we are not able to utilize more than 1 to 2 gigahertz because this layer is limiting our ability to utilize the computational capacity of the silicon device. So people are looking for alternative to these metal interconnects. So some radical alternatives people explored over the last. So if I list all the limitations of current metallic interconnect, high resistance, high capacitance and other electromagnetic interference, reliability issue, electromigration, we'll talk about it later, skin effect, 3D effect, ohmic voltage drop and self-heating because of the heat trapping. So all these problems limiting the utility of metallic interconnect, which is limiting the ability to get high computational power using high-speed silicon device. So some of the alternatives people are exploring, one is RF interconnect. Instead of metallic interconnect, can I use radio transmitter and receiver inside the IC so that you can send more signals between two receiver and transmitter using RF communication or signal modulation. Another one is using optical fiber instead of metallic wire. 3D interconnect, there is another alternative, and also people started exploring alternative to metal, carbon nanotube and graphene. So carbon nanotube and graphene, why it looked so promising at the beginning, still some people are doing research on that. Why? Because graphene can replace silicon here as a semiconductor. If you tune the property of graphene and get semiconducting graphene, graphene also has the promise of replacing the metallic conductor to overcome the challenges of metallic interconnect. So, by controlling the electrical, material and physical property of graphene and carbon nanotube, the message here is you can achieve semiconducting graphene for replacing the silicon devices, and you can very highly conducting metallic graphene to replace the metallic interconnect. So currently one of the biggest problem with the IC processing is inside the IC you have to process at least 4 different types of material: silicon, insulator, transition material and metallic interconnect. So 4 different types of materials you have to process for a tiny IC. More material processing and more step, it not only leads to interface problem, it not only leads to mismatches in electrical, mechanical, physical properties, it also leads to excessive high cost of manufacturing. So if we can find solutions where the devices as well as interconnects can be, these are the two main parts, the two workhorse in your ICs. One part is the transistor, the other part is the interconnect. Transistor is processing the signal, interconnect is carrying the signal, right? If both parts can be implemented with identical materials, your number of processing steps will decrease significantly. Ultimately, it will reduce the manufacturing cost and it will simplify the manufacturing steps. With that motivation, they started exploring options whether we can replace metallic interconnect with graphene and semiconductor devices with graphene. Now, let us look at some of the challenges of current interconnect technology, why people started looking for alternative. And this will also give us a clear idea the biggest challenge of current micro and nanoelectronics. Once again, the biggest challenge of current or limitation in current micro and nanoelectronic industry has nothing to do with silicon device. It's all about limitation imposed by interconnect line. So we have listed a number of challenges of metallic interconnect line, which is actually keeping us with limited bandwidth in current computational IC. And two of the biggest problems that relates to everything else are electromigration and skin effect at high frequency, high speed. Skin effect and electromigration. So I am going to elaborate on these two. First, let us talk about skin effect. When electrical signal flows through any conducting medium, the AC signal, they will have certain frequency, transmission frequency. So when you are sending water through a pipe, you anticipate that entire diameter of that pipe throughout the entire cross section, it will carry water. And it happens like that. But in electrical conductor, something unique happens. As you send signals at higher frequency, the signal doesn't flow through the entire cross-sectional area. Higher frequency signal tend to concentrate around the surface or the skin of the conductor. Higher the frequency, higher portion of the signal will concentrate around the periphery surface area of the conductor, and the middle area, the shaded middle area, the core, will become empty gradually, and at one point it will not carry any signal at very high frequency. So there is a shaded area of the conductor at very high frequency that will not be useful to conduct any current. Because at high frequency, electricity or current or the signal will concentrate to the skin or the surface of the conductor. That effect is called skin effect. It is the concentration of high frequency electrical signal towards the surface of or the skin of the conductor. As a consequence, the core, the central part of the conductor will carry less and less signal. At one point it will be completely depleted from any signal conduction. So now the question is, at what frequency, to what depth the core of the signal, core of the conductor will not carry any current, or to what depth signal will concentrate from the surface downward. That measure is called skin depth. That means from the surface up to this part, from all the surface, signal will be concentrating, leaving the middle part empty. No signal will be carried by that. So that is skin depth, which is famously expressed by delta. That is a function of the resistivity of the conductor, rho, and frequency, and mobility, permeability of the surrounding material, the insulator. So, as you can see, the most important property, rho, the resistivity, which determines the skin depth, that is directly related to the material property, and also the surrounding material. So now if you pick a certain material with certain resistivity, higher the frequency, skin depth will be lower. That means more and more signal will be concentrated toward the surface, leaving larger portion at the core empty or devoid of any charge conduction. And resistance of any conductor, then it becomes a function of frequency. Why? What is resistance? Resistance R is equal to rho L divided by A. Larger the cross section of a conductor, lower the resistance. Smaller the cross section, higher the resistance. So due to skin effect, what is happening? At higher skin effect, I am losing a larger portion of the conductor, not carrying any current. So all the current will be concentrated along the surface. That means the available cross section for my signal to conduct is getting smaller and smaller. Effective resistance is increasing. So resistance is a function of skin defect. As skin depth increases, resistance will increase. So resistance is no longer a constant property. It is called a function of now a frequency. So, but at what frequency the skin effect will appear? Appearing skin effect means that some portion of the core will no longer carry current. So at lower frequency, entire surface, cross-sectional surface will carry current. At higher frequency, it will start gathering, concentration will become lower. At one point along this central line, it will disappear. And then at higher frequency, it will continuously expand that shaded area, devoid of current carrying conduction capability, so it will increase. At what point the skin effect will appear, that is a portion of the core will not carry current. That is called the corner frequency or critical frequency. That frequency is given by this. So once again, because of the metallic conductors' vulnerability to skin effect, the metallic conductors' resistance, although theoretically every material should have a constant resistivity, but practically at higher frequency, effective resistance of any metallic conductor will continuously increase because of the skin effect. That means at higher frequency, it will carry lower amount of electricity because of the increased resistivity due to skin effect. So that is one of the problem. The second problem with the metallic interconnect is electromigration. So in digital, particularly digital electronics, all the signals you are carrying, either high or low, these are unidirectional signal, either signal going high or signal low. Analog signals are oscillating. These are not oscillating, it's a one directional signal, going high or going low. That means current either flowing in this direction or in this direction, depending on which signal. So if there is a one line in your IC, one interconnect line, always carrying a high control signal. Every time you turn on, it is carrying a binary 1. That means signal in that line is always flowing in one direction. One of the example is your power line. You have two lines, one is VDD, one is ground. In those two lines, every time you turn on, signal will forever go in one direction, in VDD line, one direction in the ground line, right? So now these signals are flowing through wires with a dimension of fraction of a micrometer. And atoms are also with the size of a fraction of a micrometer. So through this wire cross section, you have electrons and charge carrier moving in one direction continuously. As it is moving through the metallic layer, the individual atoms are continuously bombarded, are colliding with electrons from one direction. So if you put lots of glued element here, but if I continuously push through them again and again, 100 times, 1,000 times, gradually some of those will move in this direction, some will move more, some will move less. As a consequence, a gap or a fracture will appear. Because we are continuously bombarding, colliding electrons onto this atom from one direction non-stop. So, due to this non-stop bombarding of electrons in one direction through one line, gradually some atoms within that metallic conductor will be displaced. Some will be less, some will be more, leading to cracks, holes, or complete breakdown of continuation of the line. This movement of metallic atoms due to the bombardment of electron, this phenomena is called electromigration. Electron-induced migration of metallic atoms inside tiny piece of metallic wire. Does electromigration happens in AC line or very thick line? Yes, but in a very thick line there are billions of atoms per cross section. If one or two atoms are displaced, it doesn't matter. In AC line, if something is displaced leftward, next time it will be displaced right, because in AC line it is going this and this direction, high and low, right? So, but in DC unidirectional line, electromigration problem is severe. It is more severe in micro scale line because the whole thickness came down to few atoms. In that layer of few atoms, if one or two is displaced, a crack or a breakdown appears. If like 10 of them are displaced, then you have entire breakdown of line appears. So this is called electromigration. So among all the lines in interconnect, the lines that carry unidirectional control signal, fixed high or low for entire operation, power line, ground line, always carry unidirectional signal, those will experience higher possibility of electromigration than bidirectional line. If a particular line is carrying binary high one time, next time it is carrying binary 0, then current is actually fluctuating. At one clock cycle it is moving in this direction, next clock cycle it is moving in another direction, so it balances out. But still it will face some electromigration. So these two are very important phenomena in micro and nano electronic circuit. What is the consequence of all the challenges and limitations we have discussed in the last 3-4 slides in current metallic interconnect? The consequences are the devices are becoming smaller and smaller, from 100 nanometer to 10 or 20 nanometer to now single digit nanometer, which we are calling sub-nanometer. So as the devices are becoming smaller, they consume less power and they become faster. So the individual transistor speeds performance are continuously going down. With the individual transistors, those internal local connections from gate to source, source to drain, of one transistor inside or neighboring transistor, gate of one transistor to the source of the next transistor, those local interconnect lines connecting the gates of source and drains of individual transistor or to its immediate neighbor or closest neighbor, those local lines, we call it local lines, they're also becoming shorter and smaller. So their speed also decreasing, performance also following the similar path of the device. But the global line, those are going from layer to layer, from one side to the IC to the other side, from one core of the IC to the other core. We are calling it intermediate line or medium line or global line. Those lines are getting longer. Now they have to connect more devices in their path. So you need more global lines, and they are becoming longer. And to place more global lines side by side, you have to make them narrower, because your real estate space is still fixed for last 70 years, 2 to 3 centimeters. So within that 2 centimeter or 3 centimeter layer, if you want to put more global line like this, right? More lines, then you have to place them closer. You have to make them narrower. And since they are connecting more and more device, they are traveling more longer path, so they are becoming longer, narrower, thinner. And they are placed close to each other. As a consequence, electromagnetic or electrostatic interference from this line to this line will become stronger because they are closer. Noise from this one will interfere this one stronger because they are closer. As they are becoming narrower, means their cross section is going down, resistance is going up. As they are becoming longer, also resistance is going up, because resistance is linearly proportional to length, inversely proportional to cross section. So as a consequence, noise interference resistance of global interconnect line is increasing with the increase of device scaling or device density. So that's why what is actually happening, global interconnect delay is actually increasing with the successive scaling of technology from 250 nanometer down to 100 this comparison. So what is happening? The gap between device performance and global interconnect performance, the gate level, individual transistor, logic gate, AND gate level performance, and the global internet performance is widening. So even if you finish this task in a fraction of a picosecond, you have to just wait, because this one is running at much slower speed. So performance limitation or the bandwidth limitation of current IC is not dictated by the gate level performance or individual transistor level performance. It's because, and widening gap means more uncertainty. If you design your circuit based on the frequency achieved through the logic level or gate level simulation, that will be a tremendous underestimation of actual, right? Sorry, overestimation of actual performance, because the delay here is much higher than this delay, almost like getting like 10 times more higher than this delay. So same thing, because of the higher resistivity, higher noise interference, these global lines will consume more power. So if we compare actually what is happening, a kind of circle pie diagram, in case of total energy consumption in any IC, 50% or more of the total energy consumption are consumed by those interconnects. 33% are by the logic gate, and then the 17% diffusion, this like various type of leakage and other unwanted source of power consumption in IC. And this part is actually becoming bigger and bigger, the interconnect part. Now, within interconnect, the power it consumes by the interconnect. Now let us look at the division of power consumption in different types of interconnect. As I said, the local interconnect, those are connecting the terminals of individual transistors and small logic gates. Inside an inverter you have 2 transistors, inside a 4-input NAND gate you have 4 transistors. So internal logic gate level, transistor level connections are known as local connections. So the local clock and local signals together, they consume about 47%, and global clock and global signals other than clock, they consume more than, like currently, 51%, and 2% going here and there as a leakage. Gradually, now in the current state, they're anticipating these two together, they're moving close to 75%. The local, only 25%. And similarly, overall, this portion is increasing. It is close to 70% of the total power is consumed by the interconnect. And out of that interconnect power, close to 75% are going through global interconnects and global clock signal. So they are still not talking about local metallic connections. They're talking about, can we replace the global end-to-end long-distance chip-level connections with alternatives to metal, aluminum, or copper. So that's where they are actually exploring all these materials. So this provides you a background, what motivated researcher to look for alternative to silicon and alternative to metallic interconnect made of aluminum or copper. Now let us go back to this material we have talked about. Graphene nanoribbon, or graphene, two forms of graphene. Graphene nanoribbon and carbon nanotube. So graphene in the natural form, it comes in a planar 2D graphene sheet with atoms arranged in covalent bond in honeycomb shape or chicken net shape. If you roll is this graphene sheet in a tubular form, we get a carbon nanotube. If you cut this graphene sheet into narrow ribbon shape, we can get graphene nanoribbon. This carbon nanotube or graphene nanoribbon, they come, or this graphene sheet may come in multi-layer stacked arrangement, or if you can make a single layer, then you get single wall carbon nanotube or single layer graphene nanoribbon. If it comes in a stacked form, we get multi-layer, multi-wall carbon nanotube or multi-layer graphene nanoribbon. So graphene sheet arranged in a tubular form gives us carbon nanotube. Graphene sheet cut into narrow ribbon form gives us graphene nanoribbon. So the question is how do we achieve semiconducting property if we want to use it as a replacement of silicon device? And how to achieve metallic property if we want to use it as an alternative to aluminum and copper interconnect? So two main working components inside IC. One is the semiconducting device to process the signal and metallic conductor to carry the signals, right? So graphene's electrical and physical property, particularly we talked about physical property, the strength and everything, but electrical property depends on a very unique characteristics. A factor is called chiral angle. This is the defining property of graphene that will determine the electrical behavior of any graphene sample, whether it is in the form of carbon nanotube or graphene nanoribbon. Chiral angle determines the electrical property of graphene. So the question is now, what is a chiral angle? Now, if you look at this graphene sheet, because it's a random, let's say that you were able to generate a random graphene sheet. So, if you see for this graphene sheet, the atoms, these honeycombs are arranged along this dark red dotted line, right? Because all the atoms are symmetrical to that line. Because if you just look at a chicken net, they are arranged in this way or that way, right? So this is the central axis, the default axis of the graphene sheet. The atoms, the honeycomb or chicken net shapes, the hexagonal shapes are arranged along that line, symmetrical to that line. So that is the direction of the atomic arrangement in a graphene sheet. That is called the core, the axis. Now, You don't have any control in the, so when you roll a tube, even if you are not careful, if you roll a piece of paper, it may twist this way or this way, right? So the middle line, if you draw with a slide calipers, the middle line, middle axis of the paper, and then you physically roll it through a mechanical or other material process, the rolling axis may be slightly different from or hugely different from the actual axis, the central axis of the sheet or your piece of paper. You can try. It will not 100% aligned, right? So the rolling axis and the central axis, there will be an angle axis. So if I am able to roll it along this blue dotted line, like this from here to here, right? If I cut it here, discard this anoded portion and roll it, as shown by this dark blue arrow, I can roll it, and this is my rolling angle. This angular difference between co-axis and the rolling angle is called chiral angle. And that chiral angle defines the properties of, electrical properties of graphene. Depending on, and it is called, the value of this chiral angle is called chirality. Chirality determines its electrical property. Now look at this one. This carbon nanotube, it's just an exaggerated figure. The atomic axis and actual tube, so there is an angle, right? This is its chirality. Same thing, when you are cutting the sub-atomic scale ribbon, it's not a cloth sheet, you can just cut it. You have to do it with advanced robotics. So you can never say that your ribbon cutting direction and atomic core direction will be 100% aligned. So in this ribbon itself, maybe the atomic axis will be this, the cutting direction will be this, there will be an angle appearing, that is the chirality of that graphene nano ribbon. So the message here is, graphene sheet, whether you roll it or cut it, the cutting and rolling direction and the actual central axis direction of the atoms inside the graphene sheet, there will be an angle, and that angle is called chiral angle, and the degree of this angular displacement is called chirality. That chirality will determine the electrical property of graphene devices, whether it's nanotube or graphene nano ribbon. So, carbon nanotube or graphene nano ribbon, they provide many different advantages compared to copper or low-K electron connects. Because of its one-dimensional nature, it has very, very high electron mobility. So what is the difference between this 2D nature and 3D material? Because in 2D material, you have defined direction for electron flow. There is no way to go up and down. That gives actually its higher mobility, because you have a defined direction. There is no way for electron to jump up and down, because it's a one-dimensional, one layer thick. So that gives its higher mobility and higher conductivity. Resistance to electromigration. Why electromigration happens? Electromigration happens due to the constant bombardment of electrons on the atom from one direction. Inside metals, atoms are bonded in electrovalent bonds. The electrovalent bonds are much, much weaker than covalent bond, physically talking. From physical strength point of view, electrovalent bonds are very, very weak compared to covalent bond. That's why, because of the weaker electrovalent bond, that's why metals are good conductor, because it is easy to free up electron with less energy and force the electricity. Electricity is not flow of electron. More free electron, higher current you get. Since metals outside peripheral electrons are loosely bonded with electrovalent bond with much less voltage, you can free them up, more free electron, that's why they're called conductor. On the other hand, in semiconductor, also in graphene, you have very, very strong one-dimensional sp2 bond. That bonds are significantly stronger than regular metallic electrovalent bond. So, for electromigration to happen, you need extremely high energy electron to displace any carbon atom from its covalent sp2 bond. So the possibility of having electromigration significantly reduces if I can use those conductors made of graphene instead of metal wire or metal aluminum or copper, right? So resistance to electromigration, that is one of the biggest. So just to give you a comparison of conduction capacity of carbon nanotube versus graphene. In graphene, its current carrying capability or conductivity is 10 to the power 9 ampere per centimeter square. In copper, it is 10 to the power 6 ampere per centimeter square. So it is 1000 times higher conductivity. And tensile strength, mechanical strength is, for the identical dimension, graphene is the strongest possible material. Yes.
But to make a graphene, it's more expensive than copper.
Yes, that's has been the case as of now, but if the process matures, so then it will become cheaper. Like the very first electronic watch dial, now watch has become obsolete, smart. So Seiko 5, there was a very good watch company called Seiko 5, Seiko. So one of their model was Seiko 5. That became very, very popular in early 70s. Before you and I were born, my father had a Seiko 5 and he used it for 30 plus years because that Seiko 5 first came with a vibration-based battery, and it could re-energize, recharge itself from human body temperature. It was a revolution. So, and those watches were very expensive, right? So, but now that technology is not even like $5. You can get those type of batteries from solar energy, like even like a $3 pen have a tip with solar cell to give you the reading, right? There are ball pen, Chinese ball pen with a solar reading of temperature on the tip, and price is only $3. So as technology evolves, those processing technology matures, material separation becomes more mature, then it will become cheaper if graphene becomes a viable alternative. Initially, yes, it is cheap. Like think about all the touch screen dashboard for your car. Earlier, it was a luxury for the type of Porsche or Mercedes, right? All those sports car Lamborghinis. Now, even a $15,000 Ford, Chrysler or Kia have touch screen, right? So, because the technology became cheaper. It's like I told you, right? My flat screen TV story. I can buy a car with that price now. So now let us look at the conducting property. As I mentioned, conducting property of graphene or electrical property of graphene, and this further elaboration on this chirality. Inside graphene, in addition to chirality, inside graphene nanoribbon or carbon nanotube, metals, the atoms can appear in very regular shape. All the chicken hoops or honeycombs will be arranged in perfect line. Whether the line is aligned here or little bit tilted here, but they will appear in one line, right? Like these blocks, all one line. Maybe I can put a line this, but if the whole block appears in one line, that is called an armchair arrangement of carbon atoms. Or chicken, those hoops, it's like instead of putting a very symmetrical arrangement of the dark and lighter groups, if you put them in random order, right? So there is no line in this way, or that way. That is called a zigzag arrangement of metallic. So two things. In addition to chirality, atomic, those hexagonal shapes, they all appear in line, whether it's a vertical line, horizontal line, or angular line. There is an armchair arrangement of the carbon atoms in carbon nanotube and graphene sheet. And this is called a zigzag arrangement. Through experiment, they observed that if the arrangements of atoms and these hexagonal shapes are armchair type, it gives a metallic property. If it's zigzag, it gives a semiconducting property. And if you use common sense, actually it should be true, because still they are doing experiment. Because if you have a uniform line, then electrons can flow through easily without less collision, right? But if you have lots of obstacle, zigzag path, you have to bend and twist for the electron to move forward, right? So for zigzag arrangement, conductivity will be less. That means it is a semiconducting in nature. But there are lots of additional processing needs to be done to get truly semiconducting and to get truly metallic carbon nanotube or graphene nanoribbon. So, to summarize, the electrical property of carbon nanotube and graphene nanoribbon will depend on two important factors. Number one is the chirality, and number two is the arrangement of the carbon atoms and this hexagonal arrangement inside CNT and graphene sheet arrangement, whether it's armchair arrangement or zigzag arrangement. And based on that, we will get metallic or semiconducting graphene or carbon nanotube. Now let us look at the thermal conductivity, thermal property. The thermal conductivity of carbon nanotube is expected to be as high as 6,000 watt per meter per Kelvin. So that means it can sustain very high operating temperature, because the heat it will generate can be quickly dissipated out of the device because of its very high thermal conductivity. So heat dissipation capability of any electrical system depends on the thermal conductivity of the material used to make that system. Higher the thermal conductivity, the heat will be dissipated to the environment at much faster rate. The system can tolerate higher temperature. So its reliability will increase, also its operating temperature will increase. So graphene has very, very high thermal conductivity compared to graphene. But depending on the number of tubes, if you have multi-layer graphene nanoribbon and multi-wall carbon nanotube, because of the additional layer and in between filler material, it decreases. And some experiment shows that a generic multi-wall carbon nanotube can exhibit 1400 watt per meter per Kelvin as the potential thermal conductivity. Still is a very high.
That's why Parker Solar Probe of NASA actually used the graphene composite as a surface that is very close to.
You're absolutely right, because it has to address the thermal dissipation challenge.
Yes.
So, in in those who have some idea about material science from physics point of view, so thermal conductivity is a very, very important material property. As I said, NASA solar cells, they're using this graphene coating because they want to make sure that the solar panel doesn't get heated. Whatever heat it generates, it can dissipate faster. And thermal conductivity is always measured in terms of watt per meter per degree Kelvin. Each watt of power is ability to displace 1 meter distance for every 1 Kelvin temperature difference. So that is the thermal conductivity unit. Now let us look at the classification just of the carbon nanotube. It appears in two forms, single wall and multi-wall carbon nanotube. It is observed that most of the single wall carbon nanotube, depending on the orientation and formation, it can give both types of property. You can make a metallic or semiconducting carbon nanotube. But multi-wall carbon nanotube are mostly metallic in nature. That means they are not suitable for semiconducting device. They are mostly can be useful for conductor. But there are some ways to make some of them as semiconducting. But mostly multi-wall carbon nanotube shows metallic property. So the multi-wall metallic property, and single wall can be configured both for metallic and semiconducting. So let's look at the single wall carbon nanotube, which has the potential to be used for both. What is the time?
3:43.
Okay, 2 minutes. So we'll finish with this slide. So single wall carbon nanotube is good for both semiconducting device as well as for metallic conductor. It has a mean free path of almost 1 micrometer. For current metallic, so current micro IC, there is a very, very long dimension because copper has a mean free path of only 40 nanometer. What is mean free path? Anybody can define? Atik, can you define what is mean free path? Come on, you are a material scientist.
But I forgot.
So through any medium, when electron or any charge carrier flows, it actually experiences collision. Between successive collision, how long it can basically travel freely at ballistic speed, at the speed of light between successive collision. In copper, in any typically in copper and other metal, it is about 40 nanometer. It cannot travel at ballistic speed more than 40 nanometer because it will have a collision. So that the maximum distance it can travel through a metallic or any conducting material without having this collision is called mean free path. It will travel at the speed of light. So that means the longer the free path, the electron can travel at the speed of the light for longer distance, conductivity will be much, much higher. So that mean free path in carbon nanotube, single wall carbon nanotube is almost 1 micrometer. When we are talking about 18 nanometer transistors, it's like equivalent to like couple of 100 transistor. For this, it will travel through at light. And so that actually gives this ballistic transport property of single carbon nanotube makes it very suitable for global interconnect. So also it has one single shell tube, so it is very easy to make contact. One of the biggest challenges for carbon nanotube, why it is not yet used, is basically providing surface contact. If you have a rectangular wire or a cylindrical wire, it's completely filled, very easy to provide surface to surface contact. But if you have a hollow tube, you cannot guarantee that this surface of the tube will be 100% aligned. There will be always gap because that surface of the tube will be zigzag a little bit. So when you have a hollow tube, providing them end-to-end contact is very, very challenging. So the imperfect contact of carbon nanotube, one of the manufacturing challenge that is preventing carbon nanotube from being widely used. One of the main challenge. Now, if you compare single wall to multi-wall, inside multi-wall you're talking about multiple concentric hollow tube. And if you want to make sure that every tube is properly connected, it's a really, really daunting task. So compared to multi-wall, it is easier to provide contact with single wall carbon nanotube. So there is an advantage of single wall carbon nanotube with multi-wall carbon nanotube. So that's all for today. We will start from here. This is a pretty long lecture. It's, as you can see, it has 4 parts, talking about 4 different nanomaterials. So in the first part, we are talking about carbon graphene, and then we'll talk a little bit about molybdenum disulfide, and then we'll also talk about another one. At one point, it became very popular, but then dipped. In United States, for some reason it didn't get that much attention, but for some other countries, Europe and Far East Asia, they explored that. That is called zinc oxide.